Now let's talk about action potential, and let's jump from resting memory potential to the action potential and its importance in its role in our body. Now, let me explain you action potential. First of all those cells which have capability to go from resting memory potential to the action potential, all of them are called excitable cells. Okay, point number one. Point number two, when we stimulate a cell, what does the stimulation mean? Okay, for example, this cell is at rest. For example, I'm in this state. When I enter positive charges from different ways, this is called stimulation. This is called stimulation of a cell. Okay, now we have different ways to stimulate a cell. For example, this is a neuron, okay, and this neuron contains a lot of noise receptor or touches receptors at the end of itself. Okay, when somebody touches me, okay, or he wants to touch me, he will stimulate some channels, some touchable channels at the end of this neuron. For example, these channels are called, I've already explained all types of channels in previous lecture, okay, but anyway, this type of channel is called mechanically gated ion channel. When you want to touch someone, okay, you will put some pressure on it. When you put some pressure on these receptors, on these mechanically gated receptors, these mechanically gated will be opened. And when they're opened by your stimulation, okay, a lot of positive ions, specifically sodium, and this, for example, this mechanically gated channel is for sodium. A lot of positive charges enter to the inside of the cell. So this is one way to enter positive charges to the inside of the cell. Okay. Next way, we can enter some positive charges through stimulation of some chemical or ligand gated ion channels. For example, this is a chemical substance which is called acetylcholine that we will explain this at neuromuscular junction lecture. But anyway, when acetylcholine binds to its receptor, okay, this gate will be opened, okay, and when this gate is open, so a lot of positive charges enter to the cell because this ligand gated channel is for sodium. This is another way to enter positive charges to the inside of the cell. Okay, the next way, we can enter a lot of positive charges through a gap junction from one cell to the next cell. Okay, for example, this is a cell, okay, this is another cell, and here is a connection between them by protein, and positive charges can flow directly from this cell to this cell. Okay, this is another way to enter a lot of positive charges to the inside of the cell. Okay, so we have many ways, and we have also another way, for example, by directly stimulation of electrical currents to the cell, like Master Galvani or Volt. Okay, to stimulate the cell. Now, what will happen when positive charges enter to the cell? Now, I'm at rest. Okay, for example, this is a neuron, a typical neuron. A typical neuron, when it's during resting memory potential or when it's during resting state, the inside will be negative 70 millivolt negative. Okay, now when you enter positive charges, listen me carefully. This entering of positive charges by someone or by somebody, it causes changes in voltage of intracellular area. Okay, when you change the voltage of intracellular area, for example, this cell was during rest around negative 70 millivolt. After entering a lot of positive charges, this cell reached to negative 55 millivolt. Okay, now this point, listen me carefully. This specific voltage, at which voltage a lot of voltage gated channels are opening, this exact point is called threshold potential. Okay, now when you reach to threshold potential, a lot of voltage gated ion channels will be open. Okay, now you will go and, for example, this is a voltage gated channel for sodium, and a lot of, I'll explain it later. Okay, and for now a lot of positive charges or sodiums enter to the inside of the cell, and these positive charges carry me more near to be positive. Okay, from negative to be positive, and this step is called depolarization, because previously our cell was at polarized state, and when we lost our polarity or our negativity, so that's why this is called depolarized. D means I lost my polarity. Okay, now by same voltage by which sodium voltage gated channels were opened, okay, by same voltage potassium voltage gated ion channels will be open. Okay, and because we have more potassium concentration gradient inside of the cell, so potassiums leave the cell, and when we lose a lot of positive charges, okay, the cell becomes more negative ones again, and this state is called repolarization. This is called repolarization. Re means I retake my polarity. Okay, now before go ahead, let me explain you these voltage gated ion channels. Voltage gated ion channels are those types of ion channels which are opened by specific voltage within the cell. Okay, now the voltage, the specific point at which voltage gated channels are open, this specific point is called threshold potential. Point number 3, sodium. Let me talk about sodium voltage gated. At rest, sodium voltage gated channel has two gates. Okay, one gate is called activation gate, one gate is called inactivation gate. During resting state of all excitable cells, activation gate is always and always closed, and inactivation gate is always and always opened. But when you stimulate a cell, when you go from resting state to threshold potential, activation gate is going to open and inactivation gate is going to be closed. Okay, now during this state, that activation gate wants to be open, and inactivation gate wants to be closed. At this exact point, a lot of positive charges or sodium enters from high concentration gradient to low concentration gradient. Now, within milliseconds, activation gate is now completely open, and inactivation gate is now completely closed. Got it? Now, I cannot re-stimulate this area of the cell membrane. For example, if you touch this area, you can't stimulate this area in same milliseconds, because this area is at refractory period. How? I need these channels to become once again at this state, okay, and it needs a little bit time, okay. So that's why during depolarization and repolarization, specifically during depolarization, we cannot stimulate or re-stimulate this area due to presence of these sodium voltage gated ion channels. Now, and about potassium voltage gated channels, it has only one gate in its to the inside of the cell, and activation gate of sodium is faced to the extracellular area, and this is and inactivation gate is faced to the intracellular area. Now, let me go ahead a little bit. Now, you stimulated this point, okay? Okay. How is this stimulation transmitted from this point to this point? Okay. Transmission of this action potential or this stimulation is due to what and its okay, and how is this? Okay, now let me explain this clearly. When during entering a lot of these positive charges, they will flow to their next area also, okay. For example, they will flow from this area to this area like this. When these positive charges flow to its next area, okay, it will stimulate its next area like this. For example, this next area, this is at rest, okay. This is at rest. It's around negative 70 millivolts, okay. And when these positive charges come to this area, okay, it carries a resting membrane potential from resting state to threshold potential. And at this point, once again, sodium voltage gated channels will be opened and a lot of positive charges enter to the cell, okay. And once again, they will flow to the next area and they will stimulate their next area and they will carry their next area from resting membrane potential state to the threshold potential, okay. And from this area, once again, it will stimulate its next area, and this is called propagation of action potential, okay. And always and always, propagation of action potential is forward, not backward, because the back area is at refractory period, absolutely refractory period. And this is why this is so important, okay, this sodium voltage gated ion channels. Now for example, when we want to carry these impulses from this point to this point, now from this area we have a neuron till our back or till our spinal cord, we have one neuron, and from spinal cord up to our brainstem we have another neuron, and from this point to our cerebral cortex we have a third neuron. So how from one neuron these transmissions are passing to the next neuron, okay. Let me tell you this. Now when this positive charges reach to the end of this neuron, which is called bulb of the neuron, okay, here we have some channels which are called calcium voltage gated ion channels, and due to these positive charges, these calcium voltage gated channels would be stimulated, okay. Now when they stimulate by this a lot of positive charges, so a lot of calcium enter to the inside of the cell from high concentration gradient to the low concentration gradient. And this calcium, I'll explain them in neuromuscular junction, but anyway, this calcium will bind to these. We have at the bulb of the neuron, we have some structures which are called vesicles, and a lot of chemical neurotransmitters are stored within these vesicles, okay. So by the helping of this calcium, this vesicle is connected to this membrane, okay, to the membrane or to the end of this membrane. How? For example, we have different types of protein which are called V snare and T snares or snare proteins, and calcium comes here and binds these two snare proteins to each other, and these two snare proteins pull this vesicle to the to near it to the membrane. Okay, now when this vesicle is pulled by these snare proteins, so now this membrane will be dissolved into this membrane, and finally these neurotransmitters will be released in this synapses or in this neuromuscular junction. Now these neurotransmitters stimulate these ligand-gated ion channels. For example, I talked about it previously. Okay, when these neurotransmitters stimulate this ligand-gated ion channels, so a lot of, for example, this is for sodium, so a lot of sodiums or a lot of positive charges enter to the cell, and this next cell is stimulated from resting membrane potential to threshold potential, and action potential is carried from one, and action potential will be carried from one neuron to the next neuron like this, okay, which is called transmission of action potential. Now if, listen me careful, if this stimulation is weak and it doesn't touch our threshold potential, okay, it doesn't cause production of action potential. Keep it into your mind, and this is called sub threshold potential. This is called sub threshold potential. Okay, and here also we have a rule which is called all or none. Okay, it means when a part of a cell is stimulated or it's carried from the resting state to the threshold state, okay, so all cells have to be stimulated. It means they need to go from resting membrane potential to threshold potential, and from threshold potential to action potential. So what is the exact definition of action potential? Okay, action potential simply, okay, changing of voltage across the cell membrane is called action potential. Next, for example, when this area is stimulated, okay, this is during depolarization, and it will stimulate this next area. So now this back area is during repolarization, and this next area is during depolarization. Now this area is during depolarization, and this next area is during depolarization, and this back area is during repolarization. So when depolarization is followed by repolarization, this is also called action potential, because now cell is during action. Okay, and by the help of action potential we can do a lot of things in our body that you will know all of them step by step in physiology. For example, we can transmit signals from one part of the body to the next part of the body. When we eat something, we can transmit different types of for example, when we eat a sweet, it's transmitted to our cerebral cortex by action potential. When we smell something, it's carried from, or it's transmitted by the action potential from our nose to the cerebral cortex, and so on. And our muscle contractions are due to action potential, and also here the muscle contraction was due to action potential, which was carried by sciatic nerve of the leg of dead frog. Okay, now in some cells we have a phase after depolarization which is called plateau phase. What's plateau phase? For example, I'll explain it in full details in CVS or cardiovascular lectures, but anyway, for example, this is a muscle of heart or a cardiac cell. Okay, when you stimulate this muscle, you will go from resting membrane potential to threshold potential. From threshold potential, you will go to depolarization state. After depolarization, potassium voltage gated channels are opened, okay, and a lot of potassium enters to the cell, but with a little bit delay, calcium voltage gated channels are also open at this time, and a lot of calcium enters to the cell. So now a lot of calcium enters to the cell. For example, a lot of potassium leave the cell and a lot of calcium enter the cell, okay. So we lose a lot of positive charges and we gain a lot of positive charges also. So that's why for a moment this graph will be at plateau phase, and it helps our muscle or our cardiac muscle to pump very well, okay, to pump efficiently or pump blood efficiently, okay. Now, and after this the calcium voltage gated channel will be closed, and potassium voltage gated channels are remain open, and our cells come back to repolarization state, okay. And here is another state which is called hyperpolarization. Hyperpolarization means when you go from resting state to threshold potential, from here to depolarize, from depolarize to repolarize. For a moment, due to fast efflux of potassium ions, okay, cell is going to be more negative than its resting membrane potential, okay, and this state is called hyperpolarization, okay. And also we have next type of action potential which is called which is in heart, and we will explain it in this called reciprocal excitation of the heart, and this is due to sodium and calcium uh, leaky channels. Don't waste your time in this now. What are stabilizers? Okay, stabilizers are those things or those drugs that stable these sodium channels or block these sodium voltage gated channels. For example, calcium. A lot of calcium in extracellular area block these sodium voltage gated channels, okay. So this is a stabilizer. For example, lidocaine, okay, procaine, these are local anesthetic drugs which block these potassium sodium voltage gated channels. These are called stabilizers. And about clinic, it's so important in clinic because by the help of action potential we can do our old works in our body. For example, it causes contraction of skeletal muscles, it causes contraction of heart muscle, it causes production of heartbeat, okay, it causes transmission of different signals from one point of the body to the next point of the body. There are a lot of diseases related to it, paralysis, for example, neuropathies, and so on. And so also we have a lot of drugs related to it, specifically in cardiovascular disease or CVS pharmacology. You will study it, that we have a lot of classes of drugs, okay. After the end of action potential, okay, after applying of all or none principle to this cell, okay, there are some factors that re-establish all things, okay. For example, during action potential we we lost a lot of positive charges and we gained a lot of positive charges, we gained a lot of sodium, and we now lost a lot of potassium, okay. So now we have some pumps which are called sodium potassium pumps, and these sodium potassium pumps re-establish all this phenomena. For example, it pumps all the sodium from the inside of the cell to the outside of the cell, which we have gained it during the action potential, and it pumps all potassium from the outside of the cell to the inside of the cell. And during action potential, its work and its usage of energy will be increased 10 folds and more than 10 folds than normal, okay. That's so important. So action potential uses energy, okay. This one point. The next point, speed of action potential depends on two factors here. one factor, it depends on size of a neuron. For example, this a neuron, it depends on size of a neuron. Okay, and the next factor, the larger neuron, the fastest action potential will be here. Okay, this is one point. And next point, speed of action potential depends to myelination of neuron, myelination, and we have already studied all about myelination of a neuron. For example, in peripheral nerve tissue or in peripheral neurons, myelination is made by Schwann cell. Okay, but okay, this is a cell, and when we wrap a type of a cell which is called Schwann cell around the neurons, this is called myelination. Simply. Now, this gap between these two myelination area is called node of Ranvier. Okay, node of Ranvier. Now, we have a lot of voltage gated channel and sodium potassium pumps here in this node of Ranvier. Now, these positive charges enter to the inside of the neuron and depolarize and repolarize occurs here, and then these charges enter to the next part of the neuron and depolarize and repolarize occurs, and then these charges enter to the next part of the neuron and depolarize and repolarize occurs. And these depolarization jump from one node of Ranvier to the next node of Ranvier, and this is called saltatory conduction. Okay, the word saltatory depends to the military system. Okay, but anyway, so speed of action potential depends on these two factors. Okay, so I hope you have learned a lot of things, and please don't forget to subscribe, to like, and to comment to our videos. Have a good time till next lecture. The next lecture will be neuromuscular junctions.